Why light bends? Unveiling the mystery of gravity's influence on the massless. The statement light has no mass, yet it's affected by gravity often sparks curiosity and challenges our intuitive understanding of the universe. How can something that is weightless be influenced by the force that pulls objects with mass? This seemingly paradoxical phenomenon lies at the heart of Einstein's revolutionary theory of general relativity, offering a profound insight into the nature of gravity and its interaction with the fundamental fabric of spacetime. Einstein's theory of general relativity redefines gravity as not a force, but a consequence of the curvature of spacetime caused by the presence of mass and energy. Spacetime is the four-dimensional continuum that combines the three dimensions of space and the one dimension of time. Spacetime is not a rigid background, but a dynamic entity that can be warped and stretched by the presence of mass and energy. The more mass and energy an object has, the more it curves the spacetime around it. Gravity, then, is the result of objects following the shortest paths, called geodesics, in the curved spacetime. Light, being a form of energy, also contributes to the curvature of spacetime, albeit very weakly. More importantly, light also follows the geodesics in the curved spacetime, which means that its path can be bent by the presence of massive objects. This is how Einstein's theory of general relativity explains the bending of light by gravity. The stronger the gravitational field, the deeper the dent in spacetime, the greater the deflection of light. This phenomenon has been experimentally verified through observations of starlight bending around the sun during solar eclipses, confirming the predictions of general relativity. Our everyday experience portrays light as traveling in straight lines, seemingly unaffected by gravity. However, this perception stems from our limited observations in relatively weak gravitational fields. In the presence of massive objects like stars and black holes, the story takes a fascinating turn. Light, despite its lack of mass, exhibits a remarkable phenomenon. It bends. This deflection of light's path finds its explanation in Einstein's theory of general relativity. Unlike the Newtonian view of gravity as a force pulling objects with mass, general relativity presents a fundamentally different picture. It proposes that gravity is not a force, but rather a consequence of the curvature of spacetime caused by the presence of mass and energy. Imagine a bowling ball placed on a trampoline. The ball's weight creates a depression in the fabric, causing it to curve. This curved surface represents the warped spacetime around the massive object. Now, imagine rolling a marble across this trampoline. The marble wouldn't travel in a straight line, but would instead follow the curvature of the fabric, deviating from its original path. Similarly, light, in the presence of a massive object, travels along the curved geodesics of the warped spacetime, appearing to bend around the object. The stronger the gravitational field, the deeper the depression, the greater the deflection of light. This phenomenon has been experimentally verified through observations of starlight bending around the sun during solar eclipses, confirming the predictions of general relativity. Beyond the obvious, light's mass-like behavior, the snippet you provided hints at an intriguing concept. Light exhibiting mass-like behavior. While light TDOs, photons, technically have no rest mass, they carry momentum and energy. According to the theory of special relativity, these properties are related through the famous equation E=mc², where E is energy, m is mass, and c is the speed of light. This implies that even though light has no intrinsic mass, it behaves as if it has mass when it comes to its interaction with gravity. Recent research delves even deeper, exploring the possibility of light's self-gravity. This concept suggests that the energy momentum of light itself can contribute to the curvature of spacetime, albeit to a minuscule degree. Imagine placing multiple marbles on the trampoline. Each marble, though light, would contribute slightly to the overall curvature, influencing the path of others. While the effect is incredibly small and requires further investigation, it opens exciting avenues for exploring the intricate relationship between light and gravity. The concept of geodesics can be mathematically complex, but the analogy of the curved trampoline provides a simplified understanding of the phenomenon. A geodesic is a curve that represents the shortest path between 2 points on a surface or in a space. For example, on a flat plane, the geodesics are straight lines. However, on a curved surface or in a curved space, the geodesics are not necessarily straight. For instance, on a sphere, The geodesics are great circles, like the equator or the meridians. The mathematical definition of geodesics involves differential equations and calculus of variations. To find the geodesics on a surface or in a space, one has to use the tools of differential geometry and calculus of variations. These are branches of mathematics that deal with curves, surfaces, spaces, and their properties. One has to define a metric, which is a function that measures the distance between 2 points on a surface or in a space. Then, one has to minimize the length of a curve between 2 points, subject to some constraints. This leads to a system of differential equations, which are equations that relate the derivatives of a function. Solving these equations gives the geodesics. The analogy of the curved trampoline helps to visualize the concept of geodesics and the effect of gravity. The mathematical definition of geodesics can be hard to grasp, especially when the surface or the space is not easy to visualize. A helpful analogy is to imagine a trampoline, which is a flexible sheet of fabric stretched over a frame. If we place a heavy ball on the trampoline, it will create a dent or a curvature in the fabric. This curvature represents the effect of gravity on the surface or the space. Now, if we roll a marble across the trampoline, it will not travel in a straight line, but will follow the curvature of the fabric. This curved path is a geodesic on the trampoline. The analogy of the curved trampoline is not perfect, but it captures the essence of the phenomenon. The analogy of the curved trampoline is not a perfect representation of the concept of geodesics, because it involves some simplifications and assumptions. For example, it assumes that the trampoline is a two-dimensional surface, while in reality, gravity affects three-dimensional spaces. It also assumes that the trampoline is elastic and uniform, while in reality, surfaces and spaces can have different properties and shapes. It also ignores the effects of friction and air resistance, which can alter the motion of the marble. However, the analogy of the curved trampoline is useful because it captures the essence of the phenomenon, that gravity causes the curvature of the surface or the space, and that the geodesics are the paths that follow this curvature, including the study of gravitational lensing, where massive objects act as natural lenses, magnifying and distorting the light from distant galaxies. Gravitational lensing is a phenomenon that occurs when light from a distant source, such as a star, a quasar, or a galaxy, is bent by the gravitational field of a massive object, such as a planet, a star, a galaxy, or a cluster of galaxies, that lies between the source and the observer. This bending of light can create various effects, such as multiple images, magnification, distortion, and rings of light, depending on the alignment and the shape of the source, the lens, and the observer. Gravitational lensing can be classified into three main types, depending on the strength of the gravitational field and the alignment of the source, the lens, and the observer. Strong lensing, weak lensing, and microlensing. Strong lensing occurs when the gravitational field of the lens is very strong and the alignment is very close, creating multiple images, magnification, distortion, and rings of light. Weak lensing occurs when the gravitational field of the lens is weak and the alignment is not very close, creating small distortions in the shapes and orientations of the background sources, but no multiple images. Microlensing occurs when the lens is a small and compact object, such as a star or a planet, and the alignment is very precise, creating a temporary and asymmetric magnification of the background source, but no distortion or multiple images. Gravitational lensing has various effects on the light from the background source, such as bending, amplification, distortion, and time delay. Bending is the change in the direction of the light ray due to the curvature of space-time. Amplification is the increase in the brightness of the source due to the focusing of the light rays by the lens. Distortion is the change in the shape and size of the source due to the stretching or squeezing of the light rays by the lens. Time delay is the difference in the arrival time of the light rays from the source to the observer, due to the different paths and lengths they travel through the lens. Gravitational lensing has numerous applications and implications for the study of the universe, as it can reveal information that would otherwise be inaccessible or invisible. For example, gravitational lensing can be used to measure the masses and distances of the lensing objects. such as galaxies and galaxy clusters. By analyzing the deflection and magnification of the light from the background sources, gravitational lensing can also be used to detect and study the dark matter and dark energy, the mysterious components that make up most of the mass and energy of the universe. By observing their effects on the curvature of space-time and the expansion of the universe, gravitational lensing can also be used to discover and characterize the exoplanets, the planets outside our solar system, by detecting their microlensing effects on the light from the background stars. Gravitational lensing can also be used to explore the early universe, the formation and evolution of galaxies, and the nature of black holes, by magnifying and distorting the light from the most distant and faintest sources. This video aimed to provide a comprehensive explanation of why light, despite having no mass, is affected by gravity. It delved into the concepts of general relativity, curved spacetime, and light's mass-like behavior, offering a glimpse into the fascinating interplay between these fundamental aspects of our universe. The seemingly paradoxical influence of gravity on massless light unveils the profound complexities of our universe. It compels us to move beyond simplistic notions of gravity as a pulling force and delve into the captivating realm of curved spacetime, where even the seemingly weightless can be affected by the intricate dance of mass and energy. As we continue to explore the frontiers of physics, the mystery of light and gravity's interplay promises to reveal even more remarkable insights into the fundamental nature of our reality.